What is the primary objective of understanding quantum mechanics? Well, at its core lies the goal to uncover the fundamental laws that govern the natural world. In exploring quantum mechanics, we aim to identify principles that remain consistent across various conditions, times, and locations, and thereby providing a deeper insight into the nature of science itself. These are called invariants, and they dictate the fundamental laws governing the entire subatomic world. In today's video, you are going to learn what are those invariants and how do they behave in the quantum world. You are also going to learn why they are important and why and how these mathematical formulations lead to the physical phenomena of the quantum world that you see. My name is Shaunak and you are watching this video on my channel Physics for Students, and welcome to the 16th lesson of the Mathematics of Quantum Physics series. Now, as you understand that there might be a question in your mind that what is the ultimate goal of science? Well, the goal of science is fundamentally to measure and quantify the world around us. But what were we measuring? So by developing methods and tools to observe, analyze and record data, science seeks to create accurate representation of natural phenomena. For example, if we talk of physics, it measures distance, time, mass, velocity, acceleration, force and energy to understand motion, gravity and mechanics. If we talk of chemistry, it measures basically the temperature, concentration and the reaction rates to study chemical properties and reactions. Biology measures the growth rates of population sizes, genetic variations and biochemical parameters to understand living organisms. Astronomy measures distances, luminosity, temperature and redshift of celestial bodies to study the universe. Geology measures rock formation, fossil ages, earthquake magnitudes and mineral compositions to understand Earth's history and processes. Now, taken together, what we can see that in essence, what we can say that measurement is the language through which scientists actually communicate with the natural world, and that is the basic motto of science, that whatever we see, we try to make precise measurements. But we should also remember that the measurements are always not smooth. Now, when we say that the measurements are not always smooth, what do we mean by that? Now, let me give you a very, I would say, a basic understanding of that. Now, if we take a kind of a sphere, for example, and if we change the coordinate of that sphere, we have got a data on that sphere, which is this red area. And once we change or we stretch that sphere into an oblate spheroid, what happens if the data also stretches? Well, that is a problem, because with the variation or the change of coordinates, if the data changes, then there's a problem in terms of measurement. For example, if you have got an XY coordinate and there's a data, and if we rotate the data or the coordinate in this direction, and if the data also rotates, then there's a problem. And what is the problem? That the basic information changes, then it actually creates a problem. So the basic idea is that whatever happens to the measurement instruments or the coordinates or the periphery around where the physics is taking place, there should not be any change in terms of the measurement. So as I told you that the goal of science is measurement, but they are always not smooth. So what do we aim into? So first is that, for example, we have something which is called conservation of energy, that states that energy can neither be created nor destroyed and only can be transformed from one place to another. We have got conservation of momentum, that the total momentum of a system remains constant. Then we have Lorentz invariance, which is the laws of physics remain the same for all observers moving at constant velocity. And then we have gauge invariance, where in quantum field theory, the physical observables of a system should not change under certain transformation. And then we have got tensors, which are exotic mathematical tools, which measures the changes in a certain predictable manner. So these are all examples that the entire endeavor of science is that whatever happens, Lorentz invariance, gauge invariance, all those things actually measures that whatever the transformation changes, but not under the physical observables of a system should not change. So from here, what we can say that the tools or the mathematics that we are looking, for example, the mathematics of quantum physics or quantum field theory or relativity, what we are looking is that it will provide a language for expressing these invariant laws. So as I told you, that tensor calculus actually provides you to measure those changes. So scientists and science itself tries to identify the patterns and develop models so that we can actually predict and explain phenomena with a remarkable accuracy, and the physical things should not change whatever the changes happen. So from here what we can say, as in terms of the words of Einstein, that the laws of nature should be invariant and it should not change. Now, taking away from the macroscopic scale, if you move into the microscopic scale also, such laws do exist at the quantum level, and that is what we call that the norm of the vector must be preserved. We are going to take into account what it actually means, and it carries a profound influence in understanding quantum physics. What it tells is that the quantum states must have a norm 1, and that is, in other way we can say that the norm of the vector must be preserved. So till now what we have understood is that what is the goal of science? To measure things even there are certain changes, so that the physical things remains change. Mathematics and the entire modeling of the mathematics aims to measure those changes, and it calls that invariant laws. And in quantum world also there is something which is called the norm of the vector must be preserved. It carries, although we know, but I would like to show you that what amount of profound influence it carries in terms of the quantum world when we say that the norms of the vector must be preserved. Now, in order to imagine what is a norm, think of a vector as an arrow, and its norm is simply its length. So we can say mathematically it is a function that assigns a non-negative number, it is not a negative number, to each vector in a vector space. So what we can say that if we in mathematics the form of a vector provides a measure to for a length or magnitude. So if we can take a vector something like this, then the norm of a vector is given by this. So I've taken a wave function, there is a vector, for example psi, and then I have taken the norm. So here this psi and with the vertical bar sign, those who know the Bryan-Ket, I'm not repeating that, is actually the inner product of the vector with itself. So that is why you see the repetition. And if this psi vector is represented in terms of the components, say psi1, psi2 and goes up to psi n, then obviously the norm of a vector would be given by this, which is that by squaring that. So from here what we can understand that the norm of a state vector must be preserved to ensure that the total probability of all possible outcomes, whatever happens, of a quantum measurement must be 1. And this is a fundamental law to the probabilistic interpretation of what we call quantum mechanics. So let us consider an example. These are all things which should be taken into account with numerical examples. So if we take a simple 2D vector 3 and 4, then we can square it as the rule that I have just shown, and we get a vector norm which is 5. Now suppose I rotate this entire two-dimensional vector to 90-degree counterclockwise, and this new vector gives a negative sign because I'm rotating counterclockwise, -4. So when I square -4, it becomes 16 plus 9, 25, and square root of this is 5. So this is a very simple example to show you that the length or the norm of the vector remains the same after rotation. So this is 5 and this is 5. So from here what we can say that this is a very important example of norm preserving transformation. Now you might have a question that we understand all those things. This comes from a very basic understanding of mathematics. What is the significance in terms of quantum mechanics? Now you see that if we get the total probability as 1, so the norm of the state vector must always be 1, and it is very important for maintaining consistency in terms of calculation. What consistency? That we will explore in this part of the video. But remember that the norm of a quantum state vector, it actually shows the total probability. So if the total probability is 1, it helps us in certain quantum calculations. And what we can say is that preserving the norm actually ensures that the fundamental properties of a vector or quantum state remain consistent. Consistent in the same sense that we have just seen that it is easier to measure whatever the coordinates changes, and that is what is called the preserving the norm. So from here what we can say that what actually is norm preservation. So first of all, what we mean is that norm preservation means that as a quantum state will evolve through time, its length or magnitude remains the same. And remember, this is also what is ensured by unitary operators. I will show you certain examples. And also unitary matrices actually preserves the inner product. So if I take a unitary matrix U and it applies on a vector say V1, and V2, then the inner product is preserved, which means UV1 and W2, UV2 would be W1 dot W2 equals to V1 dot V2. So at a fundamental level, norm preservation in quantum mechanics, the example that we saw is about the conservation of probability. And the requirement of this norm vector remains 1, reflects that the total probability of all possible outcomes of quantum measurement must be 1. And the preservation of the norm is also a statement about the stability and consistency of quantum world. It ensures that the quantum systems evolve in a predictable and reversible manner over time without losing information. This is very important. It ensures that the quantum system evolves in a predictable and reversible manner over time without losing information. So here you can see what we have done, that first of all we have understood its length remains same, and unitary matrices, because they preserve the inner product. So if I apply a unitary matrix on these two vectors V1 and V2, then what it evolves, that W1 to W2 equal to V1 dot V2. So that means that if you apply a unitary matrix to two vectors and then calculate the inner product, it will be the same as the inner product of the original vectors without changing the angles between them. Now this seems very important, but it is I would say seemingly simple requirement that the norm of a quantum state must be preserved is a cornerstone of quantum mechanics. It has a far-reaching consequences to our understanding of the universe, from the nature of probability of reality to the foundations of what we call the information theory. So from here what we can say is that in quantum mechanics, states are represented as vectors, and unitary matrices describe the evolution of these states, and preserving inner product ensures that the probabilities that which will be associated with the quantum states and their outcomes remain consistent, and that is the basic objective of science, so that we can measure them inconsistently in a consistent manner. So we also know that unitary matrices also preserve the length or norm of vectors. For example, if we apply U to V and this one, then ultimately it would result into this. Now you might have a question that ultimately what is the significance of all this? So the first significance that you get is conservation of probability, which I told you that the requirement of the norm of a vector remains 1, means that the total probability for all possible outcomes would be 1. The second, what is called, is the time evolution factor. This is extremely important because as the quantum system evolves with time, the preservation of the norm also means that the stability and consistency of the quantum system is ensured. And also remember that this underpins the deterministic nature of quantum mechanics at the level of wave function evolution. The second thing is that in classical mechanics, we also use unitary matrices, and they actually preserve the length, which ensures that the physical dimensions of an object are unchanged. That means invariant under rotations. And when we talk of rotations, obviously geometry and isometries will come. So unitary matrices represent isometries and transformation and preservation of angles. So this is actually the significance of unitary matrices, which preserves the norm of a vector. However, the total norm of a vector must be preserved, and that's the reason I have also told. Let me give you a quick numerical example. So if we consider a two-dimensional vector space with a quantum state vector, for example this psi, then what we can do is that we consider the vector this one, and then what we take is this 1 by square root of 2. Then we first calculate its norm, that is squaring that, and from here what we get is this equals to 1. And now what I would like to show you is that once we get the norm equals to 1, now I'm going to apply a unitary operator u to this state vector. And here what I'm doing is that I'm getting this. And as you can understand from this equation, this part which I just highlighted in red, this box one, is what is called a Hadamard matrix. And we are going to explore Hadamard matrix in this video also, which is a common unitary matrix in quantum, I would say quantum computing. From here what we get is this one is equals to 1 by square root of 2 along with the Hadamard matrix. So once we apply u, we get this one, and further we can calculate the norm of the resulting vector, which is, again you see this shows beautifully to be 1. So from here what we can expect is that the norm is still 1, which actually shows that the unitary transformation has preserved the norm of the vector. Now as from the Hadamard matrix, we have taken 1 by square root of 2 and 1 by square root of 2. These are the two vectors. Then we applied this. I have actually skipped the matrices multiplication, which you can understand would be 1 into square root of 2 plus 1 into square root of 2. Then again 1 divided by square root of 2 minus 1 divided by square root of 2. Ultimately, it would actually come to square root of 2, 0, which will be actually equals to 1 by 0. So this is a kind of an example which actually shows you that norm is still 1, and we use a Hadamard matrix along with applying a unitary matrix also, how beautiful it preserves that norm of the vector. So from here what we can tell is that these are the few quick points. If you want, you can pause the video and take a note. The norm of a vector is actually the measure of its length. In quantum mechanics, as the state evolves, if we get a total probability 1, it helps us in calculation. Norm preservation means that the length of the vector remains unchanged. Unitary operators which preserve quantum evolution always preserve norm of vectors. And this simple example which I showed you with the two-dimensional vector also demonstrates how the norm remains constant after transformation. So till now, what we can say is that we have understood that how to calculate, and earlier videos which is there in my playlist, is that how the probability of the given system, how we can calculate. But the question is that, is it possible that if we know an initial state, whatever it is, and to transform it into any other states, is that possible? And we are going to look into this, and the answer is a big yes. And as you understand that I actually stopped the video over here, the earlier video over here, and from here we take it to postulate number 3, which is quantum operators are represented actually by unitary operators on the Hilbert space. So this was actually the clips from my last video, and I told you that a quantum operation transforms a quantum state to another quantum state. The second is that the norm of the vector is preserved. We have seen this. The mathematical representation of any quantum operation is represented by unitary matrix. This also we have seen. And any unitary matrix represents a possible quantum operation. This part also have seen. Now what we are going to see is that given a state, can we operate and see how these operations are taking place, or how we can transfer, most importantly, one state to another state. And this is going to be very interesting for the next part of the video. So for that, what we have to consider, number 1, is what are called Pauli matrices, and this is named after the famous physicist Wolfgang Pauli, who is also known for the Pauli exclusion principle and many other contributions in quantum physics. So now, what is paulimatrices? This is actually a very simple set of 2 by 2 complex matrices, and these matrices are taken into account because they take into account what is called the spin half particles, which is electrons. So we are not going to deal with spin right in this video, but we are going to see how these paulimatrices, when taken into account with quantum operations, how do they change. So there are 3 types of paulimatrices. The first one is something like this. I, then this X. I'm going to explain what are those. So the first one is called Pauli X matrix. This is the identity matrix, you understand. The next one is the Pauli X matrix. The second one is Pauli Y matrix, and then this one is called the Pauli Z matrix. We will take each of them, don't worry on that. Now, what are the properties? What are some of the very important properties of Pauli X matrix? Okay, so here you see it is written as sigma X, Pauli Y matrix as sigma Y, and Pauli Z matrix as sigma Z. Is the usual way of writing. The first thing that you need to understand is that each Pauli matrices, or the Pauli matrices, is a Hermitian. That means the matrix is equal to its conjugate transport, and this is just denoted by this with a dagger sign, as you understand. The second one is that each Pauli matrices is also unitary. That means this one, where I is the identity matrix. The trace of each Pauli matrix is 0, so we denote it by this. And the determinant of each Pauli matrix is basically -1. So these are, these are few of the properties of that. Very importantly, there is another property which is called commutation relation. And remember, the Pauli matrices do not commute with each other. Their commutation relations are given by this. And as you can understand, this one, just I highlighted circle, these are basically called Levi-Civita symbol. Now, you might have a question that why paulimatrices which are not commuting do represented by Levi-Civita symbol. I will take up paulimatrices separately in a video, and I'm going to explain you the significance of using Levi-Civita symbol over here. The anti-commutating relation, yes, because the paulimatrices satisfy the anti-commutation relations, and here again you can see that this one is basically the Kronecker delta and I is basically the identity matrix. So again I will later discuss what is this Kronecker delta and Levi-Civita symbol. The paulimatrices also have an eigenvalue of this one, +1 and -1. Most importantly, the paulimatrices in terms of the quantum physics, they represent spin-half particles. So the paulimatrices are used to represent the spin-half particles such as electrons, and as you know that spin is a fundamental property of quantum particles, and understanding it is crucial in describing the behavior of particles for quantum physics. So for example, the spin of an operator in the x direction can be represented by sigma x. We'll deal with spin separately. This is spin half particles. The second is spin operator. As you can see this with a hat sign Sx, Sy, and Z. These are spin operators for spin half particles and can be expressed in terms of the paulimatrices, which is this one. So these are some of the properties which are coming up. Then we will go into the paulimatrix operation. The next thing is, this I is equals to X, Y, and Z. Now another important thing is that for quantum gates, this is important because Pauli X not gate is where it flips the state of a qubit. Pauli Y is combining a bit flip and a phase flip, and Pauli Z, I would say, changes the phase of the qubit state. And the paulimatrices actually, I would say, they combine with other gates like the Hadamard and the C0 gates, form a universal set of gates for quantum computing, and this means any quantum computation can be constructed out of these basic gates. Also, construction for Hamiltonians are very important. So if I get, for example, if I take into the total energy, it can be represented using paulimatrices. For a spin-up particles, let us say, for example, we take the B, the magnetic field B as the Hamiltonian, then it can be written as this. You really don't have to look into these too much, but because these are very pertinent in terms of understanding the operations and going into paulimatrices, these are important. So one thing which I would like to repeat here is that this Pauli X not gate, Pauli Y and Pauli Z, the Pauli X not gate which flips it, combines Pauli Y, combines bit flip, Pauli Z changes the phase. What actually it means is that like other Hadamard and C0 gates, they form a universal set of gates. So the advantage is that any quantum computation actually can be constructed using these basic gates. And you can also represent the total energy using a Hamiltonian. Now, how do we apply paulimatrices on different quantum states? And that is what we are going to look into the next part of the video. So if we consider a qubit in the state of this 1, 0, now if we apply it to the X paulimatrix, which we have just seen, it will result into this. And what does it mean? That this transform the qubit from the state of 0 to 1, which demonstrates what is called a bit flip operation. It is a bit flip operation. So from here what we can say is that paulimatrices are fundamental in terms of quantum mechanics and quantum computing, and which represents spin operators, quantum gates, or so on. So you see how we applied very simply to the Pauli X matrix, and it changes the qubit state from 0 to 1. Now how do quantum states change when applied to paulimatrices? How does it change when applied to paulimatrices? Okay. So we will take another state which is this one. Okay. And this is the identity matrix. And applying the identity, this is the identity matrix. And this is applied on the identity matrix. So you see that applying this on the identity matrix leaves the state unchanged, isn't it? The identity matrix which I have applied. Now Pauli X matrix which I applied 1, 1. This is the X matrix. So what it happens is that this part is basically the Pauli X matrix, and it is applied. So the Pauli X matrix actually flips the state from 1 to 0. See, You see, from 1 to 0. So it has actually flipped the state from 1 to 0. So that means the identity metric leaves it unchanged. Pauli X matrix which is applied, which actually flips the state from 1 to 0. Actually I've written 0 to 1. I'm so sorry for this. This would be 1 to 0. Now if I apply the Pauli Z matrix, what happens? So Pauli Z matrix is this one. So here what happens is that this one is basically the Pauli Z matrix. So the Pauli Z matrix transforms the superposition state. This one transforms the superposition state from plus into minus. So here you see the plus one, the Z plus now got transformed into another state which is minus. This is the beauty. This is how the application happens. How about the Hadamard matrix? Here you can see this one is the Hadamard matrix, right? So the Hadamard matrix transformed the state 1, this one, into the superposition state which is this one. So it's transformed 1 to minus. So these are few of the examples. So how do these things apply and how do these things change? So from here what we can say is that if we are applying Pauli X matrix, which is often called the quantum NOT gate, it flips the state of the qubit. If the qubit is in 0, it will flip to 1 and so on. So 0 to 1 and so on. Pauli Z matrix applies a phase flip. It leaves 0 unchanged but flips the phase of 1. That means it changes the sign of the second component in the superposition state, transforming plus, it changes the componency plus into minus. So this is what Pauli Z matrices does. The second component, it changes from plus to minus. What about the Hadamard matrix? It creates superpositions. That means, again let me tell you, if we are applying H to 0 or 1, say for example H to 0 or 1, it creates an equal superposition of 0 and 1. So it creates an equal superposition of 0 to 1. Let me again repeat. If you are applying H to 0 or 1, it creates an equal superposition of 0 and 1. Remember, that is why it is superposition. We are using the AND part. And it is a fundamental quantum algorithm in order to create states where qubits are in multiple states simultaneously. So that is how, now you see the Hadamard matrix, how it beautifully creates the superposition part. So from here what we can do is that we can take a quick summary what we have learned till now. The identity matrix leaves the quantum state unchanged. The Pauli X matrix flips the qubit state. The Pauli Z matrix flips the phase of the qubit state, and the Hadamard matrix creates a superposition which is very important for quantum parallelism. Now I have been talking of Hadamard matrix, etc. Let us see into the next part of the video what is a Hadamard matrix. So Hadamard matrix is actually named after the French mathematician Jacques Hadamard, and it is a square matrix whose entries are either +1 or -1, whose rows are mutually orthogonal. Let us see what it looks like. So this Hadamard matrix was first constructed by James Joseph Sylvester in 1867. This is a kind of a Hadamard matrix, and if you want to see a Hadamard matrix of order 4, it would look like this. So you see 1, -1, -1, 1. And if you make a kind of a visualization, I would like to show you this one. If you close up this illustration, you will see that the image shows a characteristic alternating pattern of +1, which is the white, and -1, which is the black. Now from here what we can say is that this is the general I would say the classical Hadamard matrix. How do you visualize? Now in terms of quantum computing, if you talk of quantum computing, the Hadamard matrix is represented as this. Now this 1 by square root of 2, this actually ensures that the matrix is unitary. Now I'm not going to explain how. Definitely it has got a very important significance. I will take up Hadamard matrix in a different separate video, and I'm going to explain that. But what is important for today's video is that the Hadamard H gate is one of the fundamental quantum gates, and it transforms a qubit from one of the basis states like 0 to 1 into a superposition state. And this is vital, as you know, for creating quantum algorithms like Grover's search algorithm or Shor's factoring algorithm. If I show you that the Hadamard matrix for a single qubit is represented, then applying this to a qubit of 0 or 1, it creates a kind of a superposition like this. The question is that how does it create the superposition? That is something which is a question, and we are going to take up and tackle into the next part of the video. So if I take a kind of a qubit, say for example this one, and if I represent the qubit as this, I represent this qubit as this. So this is basically what is called a kind of a 2 by 2 matrix. Then we can apply the Hadamard matrix H to 0, and what we get is this one. What we get is this one. And if I do here I have actually shown the matrix multiplication. We get into this, and then we get into this part. So if I get into this part, this is something which is applying the Hadamard matrix we get. So qubit state is 0, and the Hadamard matrix shows this. And from here what we get, you see this is going to be very crucial in the next part of the video. We get a plus sign, and we get a 0 and a 1 state. So applying a Hadamard gate to a qubit initially at state 0, where we just started, we produce the superposition of a state plus. And this is this will be very interesting into the next part of the video, which I'm going to show you. So this actually shows that how we actually use the Hadamard matrix in order to get what is called a superposition. So can we do this for the next state? That is also important. That means for a qubit state 1, definitely. Let us see in a very simple explanation. So the qubit state 1 here I will represent as this. Applying the Hadamard matrix again, I have done the matrix multiplication. You can say this one. So here again we get this one. So this is another superposition, but it is with a different relative phase, which resulted to 0. So from here what we can do a summary is that if H is applied over our qubit state 0, it resulted into this. It applied into qubit state 1, it resulted into this one. So the state 1 is transformed into an equal position of 0 and 1. This is with the different signs 0, plus 1 and minus 1. So can we apply, yes, so wait for my next video where I will deal exclusively with Hadamard matrix. Now comes the phase that can we apply the Hadamard matrix on the quantum states. Let us see into the next part of the video. So first of all, the Hadamard matrix is defined, is very useful in quantum information. So first of all, what we do is that we will apply H to 0. I'm not writing the Hadamard matrix as defined. You already have seen that. So if applying H to 0 results into this. So what happens here is that the state 0, so this state, the state 0 is transformed into the superposition plus. So with this calculation we get this, and this state is transformed into this. What happens if I apply Hadamard matrix to phase 1? Then this resulted into this, and here you can see the state is in above that it transforms the state 1 into a state which is this one, minus. So all of them are getting transformed. Next, let us apply Hadamard to plus. Then it results into this, which is again this. So here what has happened? The state plus is transformed into state 0. And what if I apply it to minus? Then it resulted into this. So the state minus has transformed into the state 1. So this is a very important and a very quick example which shows actually that applying Hadamard matrix to different quantum phases actually helps you to change the phase. Now you might have heard that when Zeilinger and others got the Nobel Prize in quantum physics, that how scientists are creating superposition in order to ensure that your credit card, debit card transactions are much safer. Hackers are unable to do. This is how do they do. I mean to say, this is far more difficult, but the mathematics is quite simple. That we are using different matrices in order to define a transaction. For example, you're swiping a credit card of $100. Then how I can change that $100 into 2 quantum superposition, so that when a hacker attacks, then he or she won't be able to know which quantum phase is this transaction. So this is extremely important. So as I told you that I will be covering up in the later video. So it is very important for superposition. It is very important for quantum algorithm because it creates a lot of security. Quantum interference, by creating superposition, Hadamard gate facilitates quantum interference. We get Bell states and also entanglement. So we can say that Hadamard matrix is a fundamental tool in quantum mechanics and also in quantum computing for creating superposition, enabling what is called quantum parallelism, and forming the basis of various quantum algorithms and various other protocols. So we understood Pauli matrices, how do they apply? We understood Hadamard matrix, what do they apply? We understood the norm of a vector, why it should be preserved, and unitary matrices, their inner product. Now I will come to the final part, that all these signs or the signatures that we have seen, this is called the power of symbolic notation. This has got a unique power in terms of the symbolic notation. What is that? Now you see that sometimes when we calculate the results of quantum computing, these symbols provides a great amount of insight. I will just consider applying Hadamard matrix to plus phase, and we already know that we get this kind of a thing. So if you do the further calculation, we get this. Now I take the Hadamard matrix H inside the bracket, and I get this kind of a phase. Now when I get this, what becomes very important is that this H with the vertical bar 0, I'm just explaining you, this comes already from this. That means I can say that this part is equal to plus, and this H1 already comes from this, that is minus. I hope you're getting my point. Now let me again explain. I'm applying H over here, and I'm taking this calculation, and I'm showing this H0, which we have previously calculated, has got a plus phase, and H1 has got a minus phase, and from there we get this one. And now here you see this plus and has already come from this plus phase, because this is 1 by square root of 2, 0 plus 1, which we have earlier calculated. And this minus also comes from this one, 0 and minus. So essentially what we see is this plus has got a 0 plus 1, and this minus has got a 0 minus 1. Let us look into this in a fresh page, we will understand. So this part, as I showed you, it comes from this one, and this part comes from this one. And when we rewrite this equation, it shows this. So you see that this 0 plus 1 is over here, and this 0 minus 1 is over here. Now what is very important in this equation is that this 0, both of them have got a same sign. That means positive, obviously. But you see, one has got a positive and another negative. The question is that what does it signifies? What is the impedance? Why 0 has got a positive value, and why 1 has got a positive as well as a negative value? So now I would like to answer to this question, that you see that 0, because it has got a positive sign, that means it has got a constructive interference. In quantum physics, what we call constructive interference. And because these two have got a both positive and negative, that means the waves will come and destroy. That is why it is called a destructive interference. Just for your reference, that interference is a property of the wave particle duality, which is very inherent to quantum physics. And this is a reference of what is constructive reference, when two or more quantum states combine to increase the probability of the outcome. It creates a larger wave. And destructive interference when combines to decrease the probability, that means the waves cancel each other. Now obviously in the laws of nature, how will it cancel if both of them are positive? Now you see, this is so beautiful. I was really taken in surprise when I went through the calculations. It so shows the beautiful way nature actually works. So the 0 part is got positive signs. And how does it come? It comes from the calculation only. And the 1, which is basically the Hadamard matrix, when we are applying to 1, it is creating a destructive interference. That means the waves will cancel out. So that's all for today's video. I hope you enjoyed it. So I would like to immensely thank you for watching this video. If you have liked, please do hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can write to me on this ID, and you can subscribe to my other channel, General Relativity Explained. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. So we will continue with more mathematics of quantum physics, but a lot of things which are still to cover. But for today's video, I hope you liked it. Please do let me know your reactions in the comment box. And Physics for Students will be soon back with a lot of more exciting and wonderful videos on physics and mathematics. Till then, goodbye.